I spent 30 years staring at equations that described the end of everything, not just the end of Earth or the Sun or even our galaxy, the end of time itself, the moment when the universe runs out of moments to have. People don't like thinking about it. I understand why. We're wired to assume tomorrow will come, that there will always be another day, another century, another eon stretching ahead. The universe must go on forever, mustn't it? No, it won't. Let me show you why, and what I discovered about the final chapters of existence, chapters that will be written whether we're here to read them or not. In 1967, when I was still walking, I sat in a lecture hall at Cambridge and listened to a mathematician named Roger Penrose describe something that shouldn't exist. He'd proven that when a massive star collapses, it doesn't just compress into a dense ball, it keeps going. It collapses past any possible stopping point, past atoms, past particles, into a singularity, a point of infinite density where the known laws of physics simply give up and stop working. I remember thinking, if collapse is inevitable for dying stars, what about the universe itself? The universe began 13.8 billion years ago, in a singularity we call the Big Bang. Everything exploded outward from that point, space itself expanding, carrying galaxies apart like raisins in rising bread dough. For decades, cosmologists debated what would happen next. Would gravity eventually pull everything back together in a big crunch, a reverse of the Big Bang ending in another singularity? Or would expansion continue forever, stars burning out one by one until nothing remained but cold, dark, empty space? I spent years working on the mathematics of both scenarios. Neither was comforting. Here's what we've learned about our universe's fate and why it's stranger and more final than anyone expected. In the 1990s, observations of distant supernovae revealed something shocking. The universe isn't just expanding, it's accelerating. Galaxies are flying apart faster and faster, driven by something we call dark energy, a force we don't understand that seems to be pushing space itself outward. This ruled out the big crunch. Gravity won't win. The expansion will continue forever, which sounds like it means the universe goes on eternally. But that's not quite right. The universe will exist forever, but it won't be anything you'd recognize as a universe. It'll be something far worse. Let me walk you through what happens. Over the next trillion years, the stars will burn out. Our sun has about 5 billion years left. Red dwarfs, the smallest stars, can burn for 10 trillion years. But eventually, every star will exhaust its fuel. Nuclear fusion will stop. The lights will go out, galaxy by galaxy, until the universe goes dark. But that's not the end. Dead stars still exist. Black holes still exist. Matter still exists, just cold and dark. Time keeps going. From about 1 trillion years onward to 10 to the power of 40 years, that's 1 followed by 40 zeros, a number so large it's meaningless to human intuition, the universe enters what we call the degenerate era. Degenerate is the term for matter that's been compressed into exotic states. Dead stars become black dwarfs, white dwarfs, neutron stars, dense remnants that don't burn but still have structure. During these unimaginable eons, things happen very, very slowly. Occasionally, 2 dead stars drift close enough to collide and briefly flare with energy. Very rarely, through quantum tunneling effects, some dead stars might collapse into black holes. The universe isn't completely static, but nothing interesting is happening. No life, no light, no chemistry complex enough to support thought. Just cold objects drifting through expanding darkness. Here's where it gets truly strange. Around 10 to the power of 40 years, even matter itself starts to fall apart. Protons, the particles that make up atomic nuclei, which we've always assumed are stable, may decay. We've never observed this happening. A proton might last 10 to the 34th years before spontaneously disintegrating, but given enough time, all of them will eventually decay into lighter particles and radiation. When proton decay is finished, the universe will contain only three things: photons, neutrinos, and black holes. The photons will be stretched by cosmic expansion into wavelengths larger than the observable universe. The neutrinos will be so dispersed and low energy they might as well not exist, and the black holes will be the last structures with any complexity. Which brings us to what I discovered about black holes and why even they won't last. In 1974, I proved something that surprised everyone, including myself. Black holes aren't perfectly black. They emit radiation. Through quantum effects at the event horizon, particle-antiparticle pairs spontaneously form, with one falling into the black hole and one escaping. To an outside observer, the black hole appears to glow with thermal radiation, Hawking radiation. This radiation is incredibly faint. A black hole with the mass of our Sun would have a temperature of 60 billionths of a degree above absolute zero. It would take 10 to the power of 67 years to evaporate completely through this radiation. But it will evaporate. Given enough time, every black hole in the universe will slowly radiate away its mass until it vanishes in a final burst of energy. By 10 to the power of 100 years, a Google years, even the largest black holes, the supermassive monsters at the centers of galaxies, will have evaporated. This is the end of the black hole era. What's left? Nothing but an expanding void filled with a thin soup of photons and leptons, all moving away from each other faster and faster, stretched by acceleration into lower and lower energy states. This is the heat death of the universe. Maximum entropy, no structure, no energy gradients. Nothing can happen because there's no difference between any one place and any other place. The universe reaches thermodynamic equilibrium. And here's the truly final truth. Time becomes meaningless. Time, as we experience it, requires change. Events must happen in sequence. One moment must be distinguishable from the next. But in a universe at maximum entropy, nothing changes. There are no events. One moment is identical to the next moment, which is identical to all future moments forever. You might say time still exists in an abstract sense. The universe has an age, moments still follow one another mathematically, but practically, experientially, time has ended. There's no one to experience it, no changes to mark its passage, no way to distinguish past from future. The universe becomes timeless, not in the sense of eternal youth, but in the sense of eternal, unchanging death. I remember a journalist asking me in 2006 if this depressed me. The idea that everything, every human achievement, every work of art, every thought anyone has ever had, will eventually be erased so completely that the universe itself won't remember we existed. I told her no, it doesn't depress me. And I meant it. Still do. Here's why. The heat death won't happen for 10 to the power of 100 years or more. That's not just a long time. That's a span so vast that the entire age of the universe so far, 13.8 billion years, is less than a rounding error. It's like comparing a single human heartbeat to the age of the Earth, except the ratio is far more extreme. Humanity has existed for perhaps 300,000 years, civilization for about 10,000. We've had industrial technology for 200 years. We've known about the structure of the universe for less than a century. We're infants, cosmically speaking. What might we accomplish in the next billion years? The next trillion? We have time, so much time that it's nearly indistinguishable from infinity on any human scale. And there's something else. Something I realized while working on the thermodynamics of black holes and the arrow of time. The fact that we exist at all, that we're having this conversation now, that the universe is currently in a low-entropy state with stars and planets and life, this fact is information. It tells us something fundamental about the nature of reality. The universe began in a very special, very low-entropy state at the Big Bang. Why? We don't know. That initial condition, that particular arrangement of energy and space, created the arrow of time, the distinction between past and future. It made evolution possible. It made complexity possible. It made us possible. The eventual heat death doesn't erase the fact that for a window of time, an enormously long window, but finite, the universe was capable of producing structures complex enough to understand themselves. Stars that made heavy elements, planets that formed from those elements, chemistry that led to life, life that led to consciousness, consciousness that led to physics and mathematics and the ability to understand black holes and entropy and the fate of the cosmos. We are how the universe knows itself. For this brief cosmic summer, complexity is possible, meaning is possible, understanding is possible. The coming winter doesn't retroactively make the summer meaningless. I spent decades studying singularities, points where the equations break down, where our understanding ends. The Big Bang was a singularity. Black holes contain singularities, and in a sense, the heat death is a singularity too, a boundary beyond which time as we know it ceases to function. But here's what those decades taught me. The universe doesn't owe us eternity. It doesn't owe us meaning. The fact that everything ends doesn't make it meaningless. The fact that we have this window, this chance to exist, to think, to discover, to create, that's enough. More than enough. It's extraordinary. When I look at the night sky, I don't see the distant future when those stars will be dead. I see them as they are now, burning with nuclear fire, creating the heavy elements that make up planets and people. I see a universe that, for now, is gloriously, improbably alive with structure and complexity. The end of time is coming, but not today, not for trillions upon trillions of years, and in the meantime, we have work to do, questions to answer, discoveries to make. The universe gave us this moment, this chance to understand it before the long darkness. That's not depressing. That's the most magnificent gift imaginable. I've spent my life pushing against limits, the limits of my body, the limits of human knowledge, the limits imposed by the laws of physics. Some limits can't be pushed past. The speed of light won't yield. Entropy always increases. The universe will end in darkness and cold. But those limits don't imprison us. They define the boundaries within which meaning is possible. They give time its direction, give existence its stakes, give our discoveries their weight. The scary truth about the end of time isn't that it's coming. It's that despite knowing it's coming, despite understanding the mathematics of our cosmic mortality, we still find reasons to study, to create, to love, to keep asking questions about the universe that will outlive us by eons before finally falling silent. That's not weakness. That's the most profoundly human thing there is. The universe will end. But right now, in this moment, in this tiny window of cosmic history, when stars burn and complexity exists and consciousness is possible, right now, we're here, understanding, questioning, marveling at how extraordinary it is that anything exists at all, even temporarily. The end of time teaches us to value the time we have, not because an ending makes everything meaningless, but because it makes everything precious. I've stared at those equations for 30 years. They still describe the death of everything, and I still find them beautiful. That's the scary truth. Not that it ends, but that knowing it ends doesn't diminish the wonder of being here to know it.